Okay, thank you very much, Yeshin. Okay, so I'm here to kind of summarize all the discussion today. Amazingly, I had to come up with this presentation, last week to summarize the entire thing for today. But I think it's pretty close. Okay, so as we've all been discussing, really we're really thinking here about the future grid and how do we migrate from this present grid that's really synchronous generator dominated to a future grid that has much more inverter-based technology deployed throughout. So we've been talking a lot about renewables, wind and solar, and we know that both of those have power electronic inverter bases. But also, I just wanted to make sure people realize what else is happening. So if you think about energy storage, battery technologies, those have inverter interfaces to the grid. We're even looking at, right now, pumped hydro systems actually adding variable speed motors into the pumping part of the pumped hydro. So we're adding power electronics to hydropower plants. If you think about building loads, as this is what we're all here for, right? We're making power to generate and produce power for these loads. If you think about lighting's practically all switching to LEDs. What is LEDs? Tiny little controllable power electronics. Variable speed drives that go on motors. Even appliances, household appliances like washing machines. My washing machine at home has a big word on it, inverter-based. Like if I was a regular consumer, I would know what the heck that meant. But I'm like, ooh, it's an inverter-based washing machine. That's pretty cool. But I was looking into that. By 2021, which is 2 years away, over 60% of major household appliances will have power electronics in them. And then if you think about what's happening with the mobility fleet, electric vehicles, that's all power electronics. So there's a massive change happening, not just on the generation side, but across the entire power system. It's going toward power electronics. It's doing it for a lot of reasons, especially the efficiency gains that you get by going to power electronics, but it adds controllability into the system that we've never had before. And that's just a key thing to even think about as we make this progression toward the future. Okay, so a lot of people have talked about some of the things that are up on this particular slide. We've been looking into this for a while now, which is like how high can we get in terms of wind and solar integrated into grids? If you haven't seen this graph before, you've seen some versions of some of this data this morning, but it's system size on the x-axis all the way from a very small 100 kilowatt size island power system, pretty small, right? But all the way to the continental United States, 1,000 gigawatts of installed generating capacity. And what you see in this graph are several representations of synchronous power systems. So each of these is an actual synchronous complete power system. And then the little grayed circles there are annual energy from wind and solar. And then the little red box in there is instantaneous penetration levels that each of these systems has achieved to date. So an island power system like Cow Island in American Samoa, it's really a big oversized PV battery system, has diesel generator for backup, but it's designed to run basically autonomously for the entire year with 100% wind and solar. In that case, it's all solar. If you look at King Island, that's off Australia. It runs at 65% wind and solar. They'll run that to about 70%. They also have biofuels in that system, so they're trying to get it to 100%, but they're using a synchronous generator. The next biggest system on this chart is really kind of important, Maui. That's because that's where you kind of move away from a really tightly centrally controlled island power system to a system that's big enough to have multiple levels of voltages. And it also has generation spread throughout the entire island. That's currently running at around 34–35% wind and solar on the island, and they have run up to 76% instantaneously on that system. Not for very many hours, but they will run at that high. So there's a system that's got a control room that you would recognize as a utility control room, and they have a utility that operates the system. The next biggest one there, Ireland, that's got about a 6.5 gigawatt peak load, and that's running right now 29% wind, and they will run up to 65% what they call non-synchronous generation on the system. And I'll go into that in a couple slides here. ERCOT is the Texas system, 19% wind, and runs right now up to around 55% instantaneously. Again, that's only a couple hours in the year, but we need to kind of pay attention to where they're running. And then WEC. So the Western United States, 10% wind and solar right now, and last year they were up at a peak for 24% across the entire Western United States. Just a couple of years ago, those numbers would have been much, much lower. So these numbers are increasing very quickly. You know, one other big question we always have is like, well, continental United States, 3 big grids. How do we move from the 8% we have to over 50%? And that's what we've been talking about today is like, wow, what happens when we go 50% annual energy? What does that really look like? So let's zoom into one of these, which has got a lot of data available, Ireland. So if you take a look at this particular system, again, I mentioned before, 29% annual wind energy. But if you look at this graph, this is really interesting. This is 15-minute data from 2018 that shows the percent over on the y-axis throughout the entire year. 50% is that yellow line and 65% is the red line. But check this thing out. I mean, it is going back and forth all day long, every day, whether it's dominated by synchronous generators or dominated by inverters, every single day. So, I mean, at the end of the day, we have to have a system that works with both these technologies together. They can't, even if we talk about 100% wind and solar systems, the reality is we're going to have these systems have to work together for this major transition that's happening over time. So it's really interesting to take a close look at how much kind of variability you see in there, but we still operate the system perfectly fine in this case. If we take this exact same data and reorganize it a little bit, we get what I call the system-wide non-synchronous penetration or duration curve. So if you're familiar with a load duration curve, what we did was we took all that data, we sorted it from high to low throughout the entire year. Typically they do this for 8760 data. I just did it for the 15-minute data. But it quickly shows that basically 25% of the year, they're running a system that has over 50% wind. So pretty significant. And remember, that was only with about 30% annual energy. If they want to get that to 50% or whatever, you're going to have much higher numbers here. But it's really just interesting to take a look at this kind of data for an actual operating large-scale grid. Okay, so what does it mean to even get bigger? If you take a look at continental United States, I wanted to at least make sure people had seen some of this data as we look to even bigger grids than Ireland. So the Eastern Interconnect, the European system, the Chinese grid, all of those are pretty significant size power systems. So this was data from a report that was done several years ago called the Renewable Electricity Futures Study. But it basically looked at a couple at really high penetration of renewable cases. In this case, it's 80% renewables, but of that 80%, really only about 48–50% is wind and solar. And again, this is that same concept of kind of looking at a variable renewable demand curve, if you will, and checking different segments. And the different colors there are the East, West, and ERCOT, and the total system. And in this particular study, again, it had some interesting results. If you take a look at that green line, it was running at 59% of the hours in the year. Again, this is a total system-wide 48% wind and solar, was running over 50% inverter-based grids. And then even they had a little bit over 100, as we were talking earlier, you know, how about running grids over 100% if you have an opportunity to push that power somewhere. So not all, you know, if you're running island systems, you're kind of landlocked on where you can push power, but even on the continental US, you can move a little bit of power to the other interconnects. But it's just, again, just kind of this idea that as we really think about much higher penetration levels, we're going to see these grids with massive amounts of inverter technology. But we have to make sure that the inverters and synchronous generators work together, because throughout the year and hour by hour, these things are changing. Okay, so we talked a lot about, how the power system operates. We kind of understand how an AC synchronous generator power system operates. They synchronize together, and that's the key aspect to synchronous generators. And when they do that, they create a large-scale virtual machine that looks like it's just one giant machine shaft putting out power at 50 or 60 hertz, an AC waveform. The interconnects with induction machines or inverters are kind of this weak coupling right now because they don't necessarily provide any of that rotational inertia. And we've been talking all day really about how do we add smart controls to both wind turbines and PV systems that allow for that tighter coupling to the rest of the system. So I won't go into this in too much detail because we've been talking about it all afternoon, but obviously we would like these technologies to be able to provide a range of services, all the way from the transient and dynamic services to frequency, watt and volt var regulation. All of these are kind of defined out there as the utility system operates, and a lot of these have actual markets for people to bid into, so we need to make sure that the technologies are capable of doing that. And we've done a lot of work over the last several years looking at both, in this case, wind turbines doing this active power control and how they're able to follow automatic generator control or AGC signals from the utility, how they're actually able to do droop control, how they're able to follow a variety of different signals. So we've seen this both for wind turbines and, as Guoyi showed earlier, for big PV plants. So we know the technology can do it. I think at the end of the day, what we need to come together consensus around is how do we just lay out the rules of the road so that all these technologies work together seamlessly and that the system planners can operate the grid in a very understandable manner. So one other thing that I think Bob Lassiter brought up is, we talked a bit about bulk systems, and we have a good idea. If everything was a big bulk power system, we probably make it play by the same rules and we make it follow AGC signals. We understand kind of what its inertial response characteristics are, and it all works fine. But one of the things that we are seeing is the massive deployment of distributed technologies. So PV systems all over everybody's roofs. What do we want those systems to do? Do we want them to be passive players out there and just inject power? Do we want them to be more active participants in local voltage regulation? Things like battery systems and electric vehicles and other smart technologies, how do we want them to play? So we know we need inverters to have this smart functionality to maintain grid stability. But as we go toward millions and millions of controllable devices, what do we need to have operate that system? Because having 100 million controllable devices all go back to an ISO for control probably is not feasible. So how do you actually maintain a system like that? I don't know that we need to dive into that specifics around in this discussion today, but it's something we need to keep in the back of our mind is how do we have the system of the future work collaboratively together in this area? Okay, so I'll also mention that kind of hit, I would say, voltage and frequency control, but there are these other technical challenges which we started to get to at the end of the day today that I'll just highlight, and then we'll talk about more detail tomorrow. First one up, protection cord. Okay, so the quick understanding of protection can kind of be summarized in this slide, which is the blue line here is kind of what you get out of a synchronous generator when you get a fault. You get 6 times fault current that decays, but you get something that the protection engineer can recognize as a bad condition and respond to. Now, inverters, on the other hand, you can get all sorts of things. So you can get the red line here. If you see it, just goes up. Within a quarter cycle, detects that, trips offline, great, no fault current. Or maybe I want this thing to ride through. How many cycles do you want it to ride through? Okay, I'll have it ride through 7 cycles and then trip off. Well, so at the end of the day, I think, but there is a big limitation here is that your inverters are not going to provide 6 or 8 times fault over current because they're not going to be designed that way. So what do we do about that? At the end of the day, we probably need to come up with some kind of way of just defining this is what the fault characteristics of the inverters are going to look like so that the protection engineers can design around that. Now, they may have to come up with new protection algorithms, but still, at least if they know what they're getting, they can design around that. Whereas right now, it's up to some guy making the control algorithms in the inverters to give it, and there's no clear standard on what that's supposed to be. So do we need to actually define what this fault current characteristic from inverter-based technologies look like? Okay, other challenges. You heard a little bit of allusion to some of these. First off, black start. You know, if the grid goes down, it has to restart, and having grid forming inverter capabilities helps you out a little bit there. But do your inverters really provide enough, we call it electrical oomph, to start the grid back up, right? Does it provide the magnetizing current for your transformers? Does it do your motor starting? Can it re-energize and charge long lines? These are things that really haven't been well laid out for inverter technologies. Probably if we studied them, we could figure out solutions around that. But that's just something that we need to think about in terms of that capability. Another big topic we already talked about today, intentional and unintentional islanding. So intentional islanding, good, if it's planned and everybody agrees to it. And that's what grid forming inverters are capable of doing. Unintentional islanding is bad. And definitely, you know, going through the 1547 process, utilities are ultra concerned about this. So how do we make sure that inverters can detect problem conditions and accurately respond to those? And the last thing I wanted to mention is cybersecurity. So a lot of times we are thinking, like, as we migrate from the system that used to just run all on physics and no communications to this highly distributed but much more controllable system of the future, you know, how do we have to think about cybersecurity concerns, and what are some issues with that we need to make sure we bake into how these systems operate? Okay, so I will kind of summarize this on what I think we need to do to achieve high levels of inverter-based resources. First off, normal and abnormal voltage and frequency control. Right? We need these inverter-based resources to be able to provide us a number of essential reliability services to maintain grid operations. Some great questions around today. Well, do they all need to do this? Do some of them need to do this? How do we incentivize inverters to do this? Does it mean that all these inverters have to work off-peak power point to provide these up and down regulation services? Or do we only need 25% of them to do that? This is still a pretty open question out there. Inertial fault right-through responses. Should we just define what this needs to be for inverters? Do we make a standard out there that says, okay, inverters, if you're providing these type of services, then you need to play within these sets of rules? Do we make that a requirement, or do we just incentivize a market out there that says, hey, if you want to provide these kind of services, there's some way of getting paid for it? At the end of the day, these inverter-based resources really need to work in concert with synchronous generators. Over the next 30, 50 years, they're going to be playing with each other on the grid. They need to work together to make sure that everything works properly. Even if at the end of the day, you're going to get to 100% inverter-based systems, you're always going to have this transitional period where you got these technologies working together. So we need to think about that. That may cause some concerns because a lot of the people that do power electronics in this room will go, well, power electronics can do everything really fast. Do we really actually want it to do everything fast, or do we want it to just work together? So those are some things we need to think about. As I mentioned, protection schemes that need to work under these high levels of inverter-based resources. The ability to black start grids needs to be considered. We spent quite a bit of time over the last two presentations talking about models. So if we think about like how we've been modeling the grid in the past, we break it all the way down to modeling the physics of these synchronous generators and their characteristics with equations. But in the future, if we have massive amounts of inverters, like, what are the equations we're using? We're really modeling the control parameters that are baked into the inverters. So now we have like this mix of models that aren't exactly working the way we always had in the past, especially on the power system side. So we really need to think about, like, can you just make up rules that the inverters need to follow that map into how we do modeling and simulation? And then lastly on this list, grid codes and standards. So do we just need to write standards that define how things react to specific events? Do we need to write a standard around how we do grid forming inverters that do the infinite parallelability? Definitely, I think, you know, putting some rules out there, not necessarily dictating how it gets done, but setting the framework and rules would be helpful as this big transition happens in the industry. So I think these are definite needs. I did put in one last little thing, which was, it would be nice if these inverters could also, since they have so much computational capability and data processing ability, can they forecast their output and their local flexibility? And also, can they have this bi-directional communication to some upper level operator? Those would be very nice to have. They sure would help on how we actually operate the system of the future. I don't know if they're 100% necessary, but I think they would be nice. Okay, with that, I'll wrap it up, and we have some time for questions.
What's important is that synchronous machines or inverters, they are power conversion devices. So what you have behind there, that is important. So if you can forecast what's behind there and, you know, the controller, you have sort of the answer to what you can.
Yep. If you can forecast what the things are going to do and how they're going to respond, that's really very helpful. We don't.
You need sort of standardize the control response on some level.
I would agree. It would be, I think, nice to have a standardized control response to these variety of events that happen. Right now, we definitely don't have that. Other comments or discussion points?
Thank you. In terms of, I think you point out a very important issue that we haven't addressed so far, is protection. So what is your stand in terms of using the inverter information or signals to provide information to protect the devices?
Well, I'll just say that we as a community really need to think about how we're going to do protection into the future. There's definitely a lot of ideas out there, and I think even Chloe's about to talk, but they have a solicitation that's asking for innovative ideas in this space. So we really need to think about how we do the protection. In general, like I'll say, there are a lot of interesting ideas. We also need to think about how you do it over all these ranges of conditions, because you're never going to just have like 100% inverter and then you design your protection around that. Or, you know, how do you have it transition between full converter based and full synchronous generator based? Go ahead.
Yeah, I have questions. So in the earlier slides, you have shown high penetration level of wind and solar for a number of small and large systems, even for larger systems, right?
Yep.
The Ireland, Maui, and the ERCOT. So that means that today, the inverter-based resources are working together with the machine, right?
Yes.
So my question is not 100%, but it's pretty high up there, 75%, whatever, 60%. So what is actually the breakthrough that we need to have in this community to make it higher, even higher? Because I mean, what are the challenges today? They are already able to operate at such a high level.
Yeah, those are fairly high levels. I would agree. I mean, I was surprised when I went and dug up the numbers on those. I would say none of those are really grid forming converters, right? They're all grid following. And Ireland, which is the biggest, has the highest numbers with the biggest system out there. They they are artificially limiting that number to 65% right now. So they, as a system operator, are curtailing to keep under that number and not letting it go above that. So there are a set of challenges that we've been discussing today that get you to that higher instantaneous number. And as you try to ramp the annual average up, right? So Ireland's annual average was only 30%. If we're going to get that up to 50 or above, we're going to have to solve the challenges above that 65%. We'll top out with the system operation up there.
One thing. So those are systems with a lot of wind, which is a lot of type 3 systems that have machines and electronics sitting side by side. It's not the same as 100% energy flow.
True.
So that's another complicating aspect.
Right. I did not derate those numbers for that issue.
The sign integration of renewables actually set up some of the
So, taking a risk
The system operator feels comfortable at running those levels right now. Yeah, sure. And
comment. You already have a regular list of the things you done. I just have one more thing on your list.
okay.
I think it's important all the time to cross the data and also do the database. Either testing data in the lab or either in lab recordings. For many reasons. One reason is you get a model. You might get a model in the back. You have to get a model to reflect the physical behavior. Also use data to do the validation. Now, one big challenge, many challenges, for the data to be collected at the like a PV in the feeder level, it's very difficult. We have experience in model validation in the past more than a decade. So when you have big event, you can observe things at the level. When we get down to the two level, it's pretty much only damp or not much going on. So it's very difficult to get a dynamic event data at the lower level. So that's a big challenge for data.
Yeah, actually, the utilities really aren't going to usually have that kind of data. And actually, we may want to work with the PV inverter manufacturers that can take so much data they can do THD analysis at the inverter. But like some companies, I think, have a lot of that data. Access to the data is always a challenge.
Exactly. But they can share that.
Right. Yep. Right. FNet is a perfect example of how you just deploy a system out there to measure. Now, that's doing mostly bulk system frequency, but if we looked at a micro PMU deployment across the US, maybe that would be interesting too.
Yeah, I have a comment about today's lot of protection algorithms are designed per primary equipment characteristics. For example, for generator backup protection, we have voltage restraint over current elements. And that is a purely designed according to today's synchronous machines behavior.
Yep.
So just look at the inverter, that characteristics, there's some inverters does not output current at all when you have a fault. And some other things, due to the residue requirement, will output 7 cycles of fault current. So what I'm saying is, obviously, it seems like we need some kind of standard to guarantee future protection system will work reliably for all kind of, inverter design. And this especially comes back to, Ilu's presentation this morning. There is a critical fault clearing time, right? Regardless, all kind of situations, you have to clear your fault within that time to guarantee your system stability. So that seems point to, we have to have a standard, regarding the performance of how the inverter behaves during the fault situation. That's my comment.
Okay, thanks.
Thanks, Ben, for your talk. I wanted to ask a question about go on. I'm so intrigued by the last comment. Right. Okay, great. So you were making a comment about how fast these things are on. And I'll maybe talk a little bit about this tomorrow as well. And we talked about this in the aisle. Maybe we want to slow them down.
Right.
For stability reasons. And maybe it's a question for the whole group, or maybe you have a thought on what kinds of system level benefits there might be to keeping the voltage source controller capable of responding very quickly. Or if, as a community, it's been kind of, is there agreement on what the benefits are to the very fast timescale response, order of magnitude faster than?
Yeah, I will just say this, like, so the data that I showed there is based on some testing that we did where at the distribution level, what was happening was that the utilities were concerned about additional fault current from generators, and the inverter manufacturers were like, hey, look, we can recognize a fault in a quarter cycle and get off, so you don't have to change any of your protection, and we won't impact your fault current onto the system. That's great in one respect, but if everything was doing that, well then, would we have any fault current to clear any breakers? So it fixes one problem and it causes a different problem. And I don't think we've had what's that? Yeah, if there's no fault to clear. Well, but then you still have a downlined, and there's all these things that people can definitely come up with a huge number of scenarios that you have to address. So in general, I think we haven't had enough discussion on what makes the most sense. We've had a lot of early discussion in 1547 about what makes the most sense if we have really small amounts of inverter-based generation on the grid, and that's why the rules were written a certain way. But that's changing, and so we really need to have a more open discussion of, look, this is where the future is heading. How do we make sure that the system continues to operate reliably and we can protect it? Greg?
As a manufacturer, I don't know what the right settings are today. They'll probably change tomorrow and 5 years from now, or they may evolve over time. So, say for response time, let's say 1547 says 1 to 20 seconds response time on infection. I'm going to give you 0 to, I don't know, something else, 30. Design the equipment so it's adjustable, configurable, and then later someone who knows what the right answer is can set it to the right setting.
Yep, excellent point.
But then somebody has to do the work to set those settings.
That's right. That's right.
Right now, every utility has a different setting.
Correct. It does make it a challenge, but I think those are things we need to discuss. And hopefully tomorrow we'll have more discussion on this. Right, Brian?
Yeah, right on that note. So
okay.
Looking at the clock here, yeah, so that's fantastic to see all the lively discussion. But yeah, let's continue tomorrow, and thanks everyone for showing up. Appreciate it.